Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all my viewers out there. And I would like to shout out to all of my classmates and especially our lecturer, Madam Puan Zanaria, for teaching us this subject. And I will represent our group and will be telling you about the topic for Green's Theorem. But first, we need to introduce our team members. So, our team members has 4, including myself, Muhammad Afiq Zafran, and we have Luqmanul Hakim, we also have Haikal, and we also have Syawal Fatihah. So, moving on. Today, I would like to explain to you the introduction for Green's Theorem. But first, here's a special bonus. I will tell you the story about how Green's Theorem existed in the first place. So, as you can know, Green's Theorem, if you maybe thought that Green's Theorem is based off the color green, which is my shirt here right here, then you are wrong. Because Green's Theorem is actually from a name of a mathematician which is named by George Green. So George Green is a self-taught English mathematician who worked as a miller in the early 1800s. And in 1828, he published a little-known paper on electricity and magnetism that introduced a powerful idea, which is the behavior of a vector field around a boundary is closely related to what happens inside the region. At first, his work was completely ignored, but it was later discovered that by prominent scientists such as Lord Kelvin. Today, Green's Theorem is recognized as a cornerstone of vector calculus and a special case of Stokes' Theorem, proving that even groundbreaking math can come from an unexpected places. So, that is the history of Green's Theorem. Moving on, I would like to explain to you the introduction and the logic behind Green's Theorem. So, Green's Theorem is a fundamental result in vector calculus that establishes a deep connection between a line integral taken around a closed curve and a double integral over region enclosed by that curve. Specifically, it relates the circulation of two-dimensional vector field along a positively oriented simple closed curve to the sum of the partial derivatives of the vector field over the region inside the curve. So, for a vector field f, p xy and q xy, Green's theorem states that if p and q have continuous partial derivatives on an open region containing a region R, and its positively oriented boundary curve C, then the integral C p dx plus q dy equals to bracket qx minus py and dA. So that is what we learned from the introduction. I would like to pass on to my fellow members to explain to you based on an example question that we have prepared to you guys. Thank you.
So the next part is we present about question. So we produce 2 questions, question 1 and question 2. So in each of question, we produce 2 solutions, which is solution manual and solution command maple. So today I want to present about solution manual. So in solution manual, in the question 1, we produce equation using this theorem. Evaluate, integrate c 2x minus y dx plus x plus 3y dy, where c is the circle x square plus y square equals to 4 oriented counterclockwise. So in the solution manual, we produce 4 steps. Step 1 is identify p and q value. From the equation, we decide p is 2x minus y and then q is x plus 3y. In the step 2, we produce the general equation of Green's theorem, which is integrate c p dx plus q dy equals to double integral r qx minus py dA. And then in the step 3, we can put a partial derivative, which is we differentiate the value of p and q. So the value of q is x plus 3y. So we differentiate q in terms of x, which is we get 1. And then the p, which is equals to 2x minus y. So we differentiate p in terms of y, we get a negative 1. So we go to the step 4. The step 4, we integrate over the region R, the shaded region, which is the first thing first that we do is to find the R value, the radius value from the circle equation. From the equation, x square plus y square equals to 4. So from that equation, we get R equal to 2. So we rewrite the general Green's theorem, the general equation, which is double integral R qx minus py dA. So we exchange the general equation from this theorem to the polar coordinate, which is double integral r qx minus py r dr d theta. And then we substitute the value of qx and py, which is double integrate 1 minus negative 1 r dr d theta. So we get a 2r dr d theta. And then the range about r and theta, which is 2 to 0 and then 2 pi to 0. So we calculate, we integrate, we calculate. So we get a 4, we get a 2 pi minus 0. So we finalize the calculation, we got 8 pi.
Okay, this is the solution method for question 1. Step 1, we identify P and Q. So we get a P to x minus y, Q equal x plus 3y. Then step 2, apply Green theorem. dq dx equal to different qx, so we get 1. dp dy equal to different py, so we get the negative 1. Step 3, compute partial derivative. We integrate equal to dq dx minus dp dy, so we get the integrand equal to 2. Step 4, integrate over rq. Step 4, integrate over region R. Integrand polar equal to sub x equal to r cos theta, y equal to r sin theta, then integrate. So we get the result is 8 pi.
Okay, now let's walk through question 2 step by step using Green's theorem. The first one, we have to identify the function p and q from the line integral. From the question, we are given p equal to x squared minus y squared and q equal to 2xy. Next, we apply Green's theorems, which allow us to convert a line integral into a double integral over a region R. According to Green's theorem, the line integral around C of p dx plus q dy is equal to the double integral over region R of partial q with respect x minus partial p with respect y dA. Now, we compute the partial derivative. Since q equal to 2xy, so the partial q with respect x will be 2y. And since p equal to x squared minus y squared, so the partial p with respect y will be negative 2y. Then we substitute this into formula. We will get partial q with respect x minus partial p with respect y is equal to 2y minus negative 2y. So the answer will be 4y. So the line integral is now transformed into double integral over region R 4y dA. Next, we describe the region R. The region is bounded by the curve y equal to x squared and the horizontal line y equal to 4. From the graph, x range from negative 2 to 2 because x squared equal to 4 when x equal to plus minus 2. So the double integrals become the integrals from negative 2 to 2 of the integral from x squared to 4 for y dy dx. And then let's integrate with respect to y first. Integrate for y dy will be 2y squared. Evaluating from y equal to x squared to y equal to 4, we get 32 minus 2x power of 4. Now, we integrate with respect to x. Integrate from negative 2 to 2, 32 minus 2x power of 4 dx. We have to integrate term by term. So, it will be 32x negative 2x power of 5 over 5. And evaluating from negative 2 to 2 will be 259 over 5 minus 259 over 5. Then, finally, we obtain the final answer 500 1/2 over 5.
Okay, this is the solution method for question 2. Step 1, we identify P and Q. So we get a P equal to x squared minus y squared, Q equal to 2xy. Step 2, apply Green theorem. Qx equal to different Qx, so we get a Qx equal to 2y, Py equal to different Py, then we get a negative 2y. Step 3, we compute partial derivative. So we integrand equal to qs minus py. So the integrand equal to 4y. Then step 4, integrate over region R. So the result equal to integrate, bracket, integrate, then bracket, integrand y equal to x squared, then 4, then x equal to negative 2, then 2. So close the bracket, then the result is 512 over 5.
So that's all from our members, and we are ending our presentation here. So these are the reference as you can see in the background. And Assalamualaikum, and thank you for those who stayed and tuned together along this journey. Thank you and goodbye.